Hi, welcome you all for this video. Today we are going to discuss about multiple access schemes. So before that discussing multiple access scheme, I briefly discussed about the OSI layers. There are 7 layers in a OSI. First is a physical layer, data link layer, network layer, transport layer, session layer, presentation layer and application layer. So the physical layer will perform so many functions. So we are not discussed here because of a lot of the things we already learned from signals and system, analog communication, digital communication and error control coding. What we are discussing related in this, these are all in the subject that is related to the physical layer. Next, we will move to the data link layer. Data link layer is perform so many functions: error control, flow control, congestion control, unframing, and also media access control. Data link layer we are going to divide it as a two sub layer. One is a data link control, another one is a media access control. As we discussed, what are the functions performed by data link control? Error control, flow control, congestion control. These are functions performed by the data link control. And media access control, how to share a link. A single channel can be shared with a multiple user. A link can be shared with a hundred of user. That can be taken care by the media access control. So for accessing the channel by the multiple users, for that we are going to discuss so many methods. In that we are going to discuss here a random access protocols, controlled access protocol, and a channelization access protocol. In a random access protocol, we will discuss Aloha protocol, carrier sense multiple access protocol, carrier sense multiple access collision detection protocol, carrier sense multiple access collision avoidance protocol. In a controlled access protocol, we will discuss that reservation protocol, what is that polling protocol, token passing protocol. So then we come to the channelization. We well known that FDMA, TDMA, CDMA. So you can easily understand in a FDMA how can we share a channel with multiple users. So that is a frequency division. Okay, so if 1 megahertz of frequency is available, you can divide it with 100 numbers, then given each piece of frequency into the individual customer. There is no, there is over. Okay, nothing will be happened. The channel can be used whatever the channel is allocated by the shared by the particular things that can be used for either transmission and reception. So yeah, first we come to the random access protocol. In a random access protocol, so what happens here is a contention method. We are going to call this as a contention method also. Randomization, we create that. Okay, how can we create the randomization in between the station depending upon the protocol outcome? Okay, first we'll come to that. Here, no station is superior to the other station. No station dictates any procedure to the another station to send or not to send. In a random access or contention methods, no station is superior or supreme to other station, and none is assigned to the priority control over another. Okay, so there is no priority over any station to assign the priority over them. You have to send first, I have to send next, like that. No station permits or does not permit another station to send or not to send at each instant, at each time of time. If we have a data, the station that has data to send use a procedure defined by the protocol to make a decision either to send or not to send. So there is a every protocol is having an procedure. Okay, we should follow the procedure. That outcome of the procedure will tell you that either to send or not to send at percent of the time. Okay, what is the main so that intention of this protocol is to in the time basis, randomness created on the time basis. For example, outcome is a time. Okay, if you can toss a coin, there may be head or tail. If two stations toss the coin, if your choice is head, you can send it. Okay, your choice is tail, you can come the tail, you can transmit it. So it's a probability thing. Okay, we can may get the same probability by the two stations. There is again met with a collision. What is the major problem? In a multiple share, multiple users can share the single channel. That is a collision is a major problem. Okay, for avoiding the collision, we are going to discuss these are all the protocols. So first we will discuss the Aloha protocol. Aloha protocol, or exactly that it will define its own procedure. First of all, I can see this figure. So in this figure, each station have transmitted two frames. There are four stations are there. Station 1, station 2, station 3, station 4, like that. Station 1 can transmitted frame number 1.1 and 1.2. Station 2 transmitted 2.1 and 2.2. Similarly, station 3 3.1, 3.2. Station 4 transmitted 4.1, 4.2. We'll see So that these particular frames transmitted by the every station 1, 2, 3, 4 are collided. Okay, so that end of the frame can must join with the beginning of the frame. It's a collision. Okay, so if single bit get collided, the data get lost. And similarly like that, frame 2.2 and to 4.2 is also get collided. So for avoiding this, the protocol is defined on protocol procedure. That procedure is going to call here as a backup procedure. Here what happens, every station must obey this procedure. Okay, what is this procedure tells that? So for first iteration, k is equal to 0, make a variable k is equal to initially 0, then send the frame. After sending the time, wait timeout time. So wait timeout time. So here is an acknowledgement basis methods. Okay, every transmission is based on the acknowledgement basis method. Suppose we transmit the data, so that how much time required to know about the data is succeeded or not. Okay, whichever the packets or frames, what you are going to call, when we transmit it, wait some amount of time. That amount of time is usually is equal to that round trip propagation time. Okay, to and from distance covered, how much time required, that amount of time we will wait. That is usually the propagation time, twice of the propagation time. After sending the time, after sending the frame, we will wait how much time? 2 into tp. Okay, 2 into tp is a round trip propagation time. Once you wait this round trip propagation time, so what happens, so within the time, so we get an acknowledgement. So for survival of the packet, suppose we are not get acknowledgement. Okay, if acknowledgement is received, no problem. Okay, so that everything is over. So the succeeded of the present data, what you are going to transmit it. Suppose we are not received the acknowledgement, our data maybe get collided somewhere else. What do you have to do now? If acknowledgement not yet received, the condition is false, then iterate the k value. K is equal to k plus 1. If k is equal to initially 0, now k plus 1 is indicating 1, so that k greater than k max. Okay, k max is usually the maximum number. We said that usually 10 or 15. Suppose we fix the maximum value 15. Now at the present of the time, k is equal to 1, k greater than k max. So no, a condition is not satisfied here. The condition is not satisfied here. Then go to the choose random number or between 0 and 2 to the power of k minus 1. R is a random variable average data. It is in between 0 to 2 to the power of k minus 1. K is 1. 2 to the power of 1 is 2. 2 minus 1, 1. 0 to 1. There are two values are come. Okay. So now we have to be selected or defined or derived the TB back of time. So the back of time TB is equal to R into TP. R is the value is coming out of the, so that random variable. Okay, so TP or TFR is the propagation time or frame transmission time. Both are almost are very equal. So that amount of time each station will be wait. For example, there are two stations, then each will be out taken either 0 or 1. Suppose first station will take a 0, a second station taken a 1, then 0 into TFR, 1 into TFR. TFR may be TP may be 2 milliseconds. Now first station waits with a 0 millisecond, second station waits with a what is that? A 2 milliseconds. That waiting time will be deferred. Okay, now there is no collision happened. I don't know what happens here. Both the station can prefer 0 also. If they are preferred in this iteration 0, so then what happens, what happens, then again get collided. That will be happened. Then now come to that k is equal to 0. What is the first initialization we made? That again we retransmit the data. Okay, send a frame again. So wait 2 into TP round trip propagation time. Again waiting for an acknowledgement. If acknowledgement received in the second iterations, no problem, succeeded. If not, what happens again? You go to the k is equal to k plus 1. K will become this time 2. So then k greater than k max is 15. K is that present time is 2. It's not satisfied the condition. Then choose a random number in between, or in between 0 to k is a 2. 2 to the power of 2 is nothing but 4. So 4 minus 1 is 3. 0 to 3. 0, 1, 2, 3 are the outcome of this random variable. Now, so wait TB. TB is equal to R into TP. R into 0, R into TP is nothing but R is a number 0, 1, 2, 3. TB now either 0 millisecond, 2 millisecond, 4 millisecond or 8 milliseconds. Okay, you can prefer your one. Here also maybe you can two people or multiple users can take the same value. Again they have taken the same value, they met with a collision. So here is what we are happened here. We are not eliminating the collision 100%. We avoid the collision some extent. So this procedure we are going to call as a backup procedure. Okay, so now come to that one problem. We will calculate the propagation time. So first understand the problem. I will read the problem. The station on a wireless Aloha network are a maximum of 600 km apart. Okay, there's a distance between the two stations is a 600 km apart is there. If you assume that signal propagate with a light velocity that is equal to the 3 into 10 to the power of 8 meter per second, then we want to calculate the time required to transmit a data from that station to that station with the velocity. We know the relation between the velocity and time and distance. TP is the propagation time, distance over the velocity. 600 meter, kilometer is there, we can convert it into the meter. It becomes 600 into 10 to the power of 5. When you convert it into the meter, divided by 3 into 10 to the power of 5 meter per second. Now TP is the 2 milliseconds. Now come to that. For k is equal to 1, so previously what we are going to see is that a random r we calculated, so if k is equal to 1, the r ranges from 0 to 1. So TP we know that the station needs to generate a random number with a value of 0 or 1. This means that TB is either 0 millisecond or 2 millisecond. I think you understand that. TP we calculated initially. The propagation time we calculated based on that what? A distance what you are going to given and a velocity what you are going to given. Now, so k value, k value initially k value is 0 as per the previous protocol backup procedure. Now k will be iterated until not it gets succeeded. Okay, so it will be succeeded in the first iteration, no need to problem. This is a straightforward case. Okay, if not it gets succeeded, k will be iterated, k will become 1. In this case, that r become 0 and 1. The backup time is equal to can multiply with 0 to what is the TP, 1 to TP we calculated 2 milliseconds. Now waiting time in our random protocol, random experiment, either is a 0 millisecond or 2 milliseconds. If 4 stations or 2 stations, they all may get the 0 milliseconds, they all may get the 2 millisecond depending upon the random experiment. Now k is equal to 2. For example, k is equal to 2, what happens that r is equal to 0 to 2 to the power of k minus 1. K is equal to 2 to the power of 2 is nothing but a 4. 4 minus 1 is 3, 0, 1, 2, 3 are the random variables. This means that TV can be multiplied with 0 to 2 millisecond, 1 to 2 millisecond, 2 to 2 millisecond, 3 to 2 millisecond. It can be a 0 millisecond, 2 millisecond, 4 millisecond, 6 millisecond based on the random variable. So similarly for k is equal to 3, so that r values in the set 0, 1, 2, 3, 4, 5, 6, 7. This means that TP can be 0 millisecond, 2 millisecond, 4 millisecond, like a 6 millisecond, 8 millisecond, 10 milliseconds, 12 milliseconds, and 14 milliseconds. 14 milliseconds because of 7 into 2 milliseconds. So if k is greater than 10, okay, otherwise k is greater than k max. K max is 10 or 15, the maximum number. Even after 10 iterations, your data not yet gets succeeded, then maximum collisions occur in this channel. You come out of the operation, you abort the operation presently, wait long amount of time, then resume your operation. That's the way of doing in the Aloha protocol. So in an Aloha protocol, that throughput and vulnerable time is very much important. So vulnerable time in which collision happens. Okay, how can you define the vulnerable time? The time in which collision happens, otherwise we can say in another way. So the time required to inform all the stations so there may be a collision, that we are going to call as a vulnerable time. You can understand here. So what is that vulnerable time for a Aloha protocol? There are station ABC. Okay, station ABC. A can transmit it at a time T. Even B can transmit it the previous T minus TFR. Every TFR is the frame transmission period, right? So at the T plus TFR, A will be finished. Okay, before that T plus TFR, C already get transmitted. Then we are going to see that whatever the time is there here, that is from year to year. So that is an vulnerable time. Is that twice of the frame transmission period. This amount of time is required to tell each and every station so there may be collision. Okay, so that we are going to call as a vulnerable time. Next we'll see the throughput of the system. The throughput of the Aloha protocol, which gives to that formula S is equal to G into e to the power of minus 2G, where G is the load. Load is nothing but how many frames have to be produced by the particular station during the frame transmission period. Is nothing but TFR is the frame transmission period. This amount of time in which how many how many frames has to be produced by the station. That is also a matter. For example, here G is equal to half, which gives the maximum throughput. Okay, Aloha protocol which gives the maximum throughput, that is also 0.184. It is nothing but 18.4%. That is G is equal to half, load is equal to half, means half of the frame must be produced by the each and every station, then only we can achieve the maximum throughput, that itself 18.4% in the Aloha protocol. Next we'll see that on problem, a pure Aloha network transmit 200 bit frame. Every frame is often 200 bits on a shared channel of 200 kbps. Okay, speed of a transmission of that 200 kbps. What is the throughput if the system all station together produces 1000 frame per second? Is a bit, and a B bit 500 frames per second, C bit 250 frames per second. Okay, first we will calculate the transmission time, frame transmission time, TFR. Okay, 200 kilometers is the distance, 200 kbps is the speed of transmission. Then how much time required is a 1 millisecond is the TFR. Means in a TFR time, how many frames as produced by the each and every station, that is the load. Okay, 1 millisecond is the frame transmission period. Every 1 milliseconds time, how many frames as produced by the system? If the system creates 1000 frames per second, right? 1 second, 1000 frames. This is 1 frame per millisecond. For 1 millisecond, how many frames? 1 frame has to be produced by the system in a 1 millisecond. Then what will be the load? Load is equal to now 1. G is equal to 1. Okay, can you understand now this? So we'll see frame transmission here we are going to calculate it here. 200 is the what is that? Number of bits we need to be transmitted. Okay, 200 kbps is the speed of transmission. Okay, how much time required to transmit one frame, 200 bit frame with the speed of 200 kbps? Obviously, it's a 1 millisecond. Okay, my question is now, in an 8 bit, 1000 frame has to be produced per second. What is the throughput? Okay, if the system produces 1000 frames per second, how many frame it has to be produced in a 1 millisecond? Okay, 1000 frames, 1000 1 second. Okay, for 1 millisecond is in 1 frame. Then G is equal to 1, load is equal to 1. As per the formula, S is equal to G into E to the power of minus 2G, which gives the throughput that is equal to that 0.135. So this is the throughput for the first case, A case 0.135, that is 13.5%. It's nothing but out of 1000 frames, 135 frames only survives. Remaining frames are collided. So next case we'll see that. In the second case, if the system creates 500 frames per second. Okay, I think you're able to know that what will be the 1 millisecond, how many frames has to be produced. For 500 frames, 1 second. For 1 millisecond, half of the frame has to be produced. Half of the frame has to be produced by the system in an 1 millisecond, and G is equal to G is the load is nothing but half. Half of the frame as produced by the system during the frame transmission period. In this case, S is equal to G into E to the power of minus 2G. S gives the maximum throughput, that is 0.184, 18.4%. It's only the maximum in this system Aloha protocol. Then out of 500 frames, if you can multiply with the 0.184 to this, 92 frames are get survived. So out of 500 frames, if you can choose half is the load, means 500 frames per second it has been produced. Okay, so we can continue that. That is the G is equal to half of the frame has to be produced during the frame transmission period. That gives the when G is equal to half, then only the maximum throughput you can achieve, that is a 0.184, 18.4%. Out of the 500 frames, only 92 frames are get survived in this case. In the third case, 250 frames per second. Now we can easily able to say that 1 millisecond, how many frames has to be produced by the system is 1 by 4 or fourth of the frame. Okay, quarter of the frame has to be produced during 1 millisecond. That is the load. G is equal to load. Load is nothing but how many frames has to be produced by the system during frame transmission period. Frame transmission period we calculated, that is 1 millisecond. Then compare with 1000 frames per second, 500 frames per second, 250 frames per second. Then load is in this case 1 by 4. Now put the for that particular g value into the formula. S is equal to g into the power of minus 2g. Then S gives the 0.152, 15.2%. So if out of 250 frames, only 38 frames are survived. So this is the solution for this problem. Next we'll see slotted Aloha protocol. Okay, in a slotted Aloha protocol, we can make time slots. Okay, so time slots, the time is equal to that frame transmission period. Okay, how much frame transmission required to transmit a frame from one location to the another location, source to destination, TF for slots. Okay, every station has to transmit its data at the beginning of the time slot. Suppose they have missed the time slot, beginning of the time slot, they have to wait for the next time slot. It keep on continues that. Even here also that collision will happen. So okay, how can the collision will be happen? We can see every stations can transmit it 2 frames. Station 1 can transmitted frame 1.1 and 1.2. Station 2 transmitted 2.1, 2.2. Station 3 transmitted 3.1, 3.2. Similarly, station 4 going to transmitted 4.1 and 4.2. See, this is the collision happens. Okay, so these two locations, that particular collision will be happened by, so station 2.1 frame collided with a station 3.1 frame. Similarly, 1.2 the frame transmitted by the station 1 can get collided with the what is that 4.1 frame. So here we'll see that what will be the vulnerable period and throughput. The vulnerable period here is then TFR itself, because that amount of time required to tell all of the stations there may be collision, or maybe in which period the collision will be happened. The throughput of the slotted Aloha protocol, which gives the formula S is equal to G into e to the power of minus G. Okay, where G again is the load. Similarly, what you are going to discuss in the pure Aloha protocol, G is a load. How many frame has to be produced by the system during the frame transmission period? Here, the maximum throughput here, so 0.368 when G is equal to 1. The previously G is equal to half of the frame has to be produced by the system during the frame transmission period. There we can get the maximum throughput of 18.4% only. Here we are going to get the maximum throughput of 0.368 is nothing but a 36.8% when G is equal to 1. One frame has to be produced by the system during frame transmission period. We'll see again. It's a vulnerable time that is equal to the TFR, time in which collision happens, that has to be indicated to the all other stations. Okay, again we solve the same problem in a case of a slotted Aloha protocol. I will read the problem. A slotted Aloha network transmit 200 bit frames. Okay, every frames is having 200 bits on a shared channel of 200 kbps. Okay, the channel speed is of 200 kbps. What is the throughput if the system all stations together produces 1000 frames per second, 500 frames per second, 250 frames per second? The problem all is same as the previous one. The only thing is here we are going to discuss with the slotted Aloha protocol. The previous was an pure Aloha protocol. The first thing we can calculate the TFR, frame transmission period. How can you calculate the frame transmission period? Frame transmission period is calculated how many bits of frames is there, then what is the speed of transmission. 200 bit frame need to be transmitted with the 200 kbps speed, then 1 millisecond is the frame transmission period. We can calculate the throughput of the system. If system creates 1000 frames per second, then how many frames it has to be produced with 1 millisecond? Then it has to be produced one frame with 1 millisecond. Then G is equal to 1, load is equal to 1. As per the formula for a slotted Aloha protocol, S is equal to G into e to the power of minus G. S gives the 0.368. This means that it will be the maximum throughput. Okay, 36.8% means 1000 frames you transmitted, 368 frames only survive. Remaining frames will be collided. Okay, so next in the second case, the 500 frames has to be produced by the system. Then load is equal to G is equal to how many frames it produces for an 1 millisecond. Is half of the frame has to be produced within 1 millisecond. That is a load. Put the formula. S is equal to G into e to the power of minus G, which gives 0.303, 30.3%. Then can multiply with the 500, which gives 151. What which gives with multiply with the 500, out of 500, how many frames get survived? Only the 151 frames out of 500 will be probably survive. Similar in the third case, 250 frame per second. Then load is equal to what? Is 1 by 4, right? Load is equal to 1 by 4 means quarter of the frame produced by the system during 1 millisecond. Then G is equal to 1 by 4. Then put the formula S is equal to G into e to the power of minus G, which gives 0.195, 19.5%. So can multiply with 0.195 into the 250, which gives how many frame probably survive with, so 250 frames. Okay, so this is okay, this is what related to the problem. Next we'll see what is the space time model for a CSMA. First of all, we discuss what is a CSMA. I will tell you some important slide for this. Can easily can understand by this one. Okay, so you can look so this one carefully. It gives maximum information about the carrier sense multiple access collision. Okay, carrier sense multiple access protocol. So carrier sense multiple access protocol, here the based on the concept listen before talk. Okay, so first we want to be listen who is talking on the other side, otherwise there may be mismatch. The same thing will be happened before you transmit it, sense the media. Okay, sense the channel. The channel gives the three states, either busy state or idle state or maybe collision state. Okay, how can you identify idle state, busy state or maybe collision state? The carrier energy levels. Okay, carrier energy level, someone is transmitting, some carriers are present. Okay, suppose once you sense the media, can come with a three outcome, either zero energy level, carrier energy level, twice of the carrier energy level. Okay, so it is a zero carrier energy level in this, that then indicating his channel is free. For example, after sensing, which gives the carrier energy level, okay, so that equal to that some carrier energy level. So then we mean that say someone is transmitting. Okay, no need to transmit. Okay, so that's what actually, if zero energy level we are getting, the channel is free. Carrier energy level we are getting, channel is busy. Suppose we are getting the twice of the carrier energy level, then indicating that there may be collision. No need to transmit 8% of the time. Wait longer amount of the time. Later we will transmit it.